I want to take a look at this question, and the question statement is a bit long, so pause the video, read it, and come back when you finish. Alright, part A. We want to find the temperature required for the steel bars to fit the pins. That means the delta of steel is equal to 0.5, and this is thermal strain. So we know that thermal strain delta is equal to alpha delta T L. So we know this is 0.5 millimeters, and alpha for steel is 11.7 times 10 to the negative 6, and the difference in temperature is what we're trying to find. L is 1.995 meters because it's made 5 millimeters short, so that's the length of steel. And then simply solve for temperature. So we get 0.5 over 11.7 times 10 to the negative 6 times 1.995. I made a mistake here because everything should be in millimeters. So technically I have to say 1999.5 is the original length. Okay, now everything is in millimeters. Then plug this into your calculator. 0.5 over 11.7 times 10 to the negative 6 times 1999.5. Get the temperature change is positive 21.37 degrees Celsius, and that will be our answer to part A. Now part B is more complicated than part A. Part B, we're asked to find the stress in steel and brass bar. Oh, just the brass bar. Okay. Part B will have to start from a strategy. I want to say that at the end, the assembly have the same length, while brass is only stretched by a distance of delta. Whoops. The steel bars are stretched 0.5 millimeters more than delta. Cool. This is our observation and our key to solve the problem. Next, we'll start with statics. And for statics, we will need a free body diagram, so we're also going to call this model. And our model would be a section of the side view. So the brass receives a force 25 kilonewtons to the right. I'll define this as the X and this is the Y. Now we have two steel forces pulling back to resist the 25, along with the change in length because it's fitted after the temperature decreased. Brass is also going to react to the 25 kilonewton force by pulling backwards. So we have two steel forces and one brass force. From this free body diagram, we can derive that 2Fs plus 1Fb is equal to 25 kilonewtons. And this is our first relationship. Next, we move on to geometry. We want to look at after everything is stretched, what's the geometry looking like. So after stretch, so this is the length after stretch, but to draw on top of this, one sec. Okay, this distance is the original length of steel. So steel totally stretched this distance, call that delta S. This distance is how much brass is stretched by. So we can call that delta B. We know from strategy that delta S plus 0.5, no, delta S is 0.5 more than delta B. So we can write this. Let's write steel here, and brass here. Okay, this is our second relation. Our third category will be displacement analysis. This is where I can say the change in length in steel is equal to the P delta relation, which says P, the stress in steel, so I mean the force in steel times original length of steel, all divided by the area of steel, cross-section area, as well as Young's modulus of steel. Similarly, delta B, displacement of brass, is just the same relation but with all subscripts turned into B. Now we can put all these together and sub into equation 2, which will give us that FSLS ASES is equal to FBLB over ABEB plus 0.5. Okay, now we can also substitute that Fs is actually equal to 25 kilonewtons minus Fb all over 2. This is actually just rearranged equation 1 from statics. So we can sub that in, 25 minus Fb. I can put the 2 below it. 2 AS ES equal to FB LB Let's try to simplify this. So 25 LS over 2 SES minus FB LS 2 ASES Now I want to rearrange the two sides so all the FBs go in together one place. So FB big brackets LB over AB EB plus LS 2S 2AS ES is equal to 25 LS 2AS ES minus 0.5. All I did is move 0.5 to the other side and move this part to the other side. Okay, so I can technically just put all of this on the denominator on the right side, but that will make it look quite difficult and intimidating. So let's plug in some numbers here and start solving it. I know that LB is 2000 millimeters, also known as 2 meters. AB, now let's solve for A and revisit the diagram we are given. So I will copy the diagram, paste it here. Okay, cross-section area of brass is equal to 15 millimeters multiply 40 millimeters. Type that into the calculator, and that gives me 6,000 millimeters squared. A of steel. Now this is the area of each piece of steel. That would be 5 times, sorry, this is 40, so this needs to be 600 instead of 5 times 40. It's 5 times 40, which is 200, exactly 1/3 of brass's area. Okay, so 2000 over AB, which is 600, multiply the elastic modulus of it. I can just call that 105 gigapascal plus 1999.5 over twice 200. Steel has an elastic modulus of 200 gigapascal. On the other side we have 25 1999.5 over 2 AS, which is 200, as well as 200. Now FB will be given in kilonewtons because we have mm squared and gigapascal. This combination will give you gigapascal. If you're not convinced, give it a try. But I'm just telling you it works like that. Okay, let's do more calculator work. 2000 times 600 times 105 plus 1999.5 over 2 times 200 times 200. That gives me FB multiplied by 0.056797397. The other side is 25 1999.5 over 2 times 200 squared. I get 0.64284375-ish, which gives me FB is equal to 11.012. No, I forgot one important thing. I forgot to drop the 0.5 down. So let's recrunch that. 0.6428. There you go. Then we get 2.2003 kilonewtons. Now let's look back to our free body diagram. FB is pulling out, so FB is actually in tension. It will make sense because in this configuration, nothing is really in compression. They all respond to the applied force P, which is in tension, so FB must be in tension. We are near the answer that we want to find. The last step, we want to say the stress, the normal stress in B, brass, is equal to positive F for tensile over the area of B. That means 2.2 kilonewtons over 600 millimeters squared. This will give me an answer of gigapascal. I mean, yes, gigapascal, but that doesn't really tell me anything, so let's multiply 1,000 and you will get 3.666, rounded last one to 7 megapascal tensile. And therefore, normal stress in brass is 3.667 megapascal bracket tensile. Okay, last step is reflect. What do we notice here? We worked off the assumption that the steel is not strong enough to pull everything back and make the brass be in compression. We're assuming that P was strong enough that steel didn't really have the ability to stretch everything back. So we can note that we assumed that P is significant enough to stretch out the steel, so brass is in tension. Otherwise, we would find that FB is negative meaning it is in compression. There you have it.